Good afternoon. This is our seventh lecture, and today our ambition is to cover the topic of the occurrence of accidents in general. This is part of what's called system analysis, and you'll find that we have very, very little knowledge about how to expect the accidents to occur. But we have ideas on some kind of empirical ways of predicting that accidents can occur. Hello? Hello? Sign this, please. All right. So accidents are part of human interaction with nature. And we suggested that in the previous chapters that natural accidents can cause eventually the failure of devices that we use as humans. It could be caused by a natural event, a tsunami, an earthquake, a hurricane. It can be caused by human error, and it can be caused by equipment failures. So in that case, it's important for us when we build any kind of human structure so understand how accidents can occur. And we tried that by setting up some criteria in terms of what are the scales that we use at different locations and environments where accidents have occurred in the past. And when we design structures on those locations, then we take that into account. There is a quote here that I would like to bring to your attention. Okay, I jumped too far here. That is what's called the Murphy's Law. You all have heard about Murphy's Law. And it suggests that if given enough time, anything that can go wrong will go wrong. That's called Murphy's Law. So if you create the circumstances that do not avoid Murphy's Law, accidents are going to happen. Albert Einstein came up with another suggestion about the occurrence of accidents. Quote, as far as the laws of mathematics refer to reality, they are not certain. And as far as they are certain, they do not refer to reality. And that is going to suggest to us that when we calculate some probabilities of occurrence of accidents, we cannot determine really an exact number. There will always be associated with uncertainty. And we described last time, if you missed the class, you can see it on the internet, read it, that we have two types of, I don't need Alexa, two types of uncertainties. One that we call randomness, and that has to do with the observations that we make about different devices and any kind of circumstances that society goes through, being economic or social or natural events. And there is another form of uncertainty that we would call fuzziness, and that has to do with the meaning that we associate with those measurements in general. The occurrence of accidents follows system theory. That's a whole field of science by itself, where people study systems and how they interact. System theory has part of it what's called chaos theory or complexity theory. If you want to expand more knowledge, then you have to go to access literature on system theory. System theory tries to address the reasons for the occurrence of disasters, earthquakes, social upheavals, as well as movements of the financial markets, like stock market collapse would be part of systems theory. A philosopher at Harvard University, he wrote a text. The title of it is Complexity and Collapse. The more we build a complex system, the more the possibility of their collapse through accident. And I'm going to read that whole paragraph because it's very illuminating up to the point. So we are dealing with complex systems that are made up of a very large number of interacting components that are asymmetrically organized. This means that their construction more resembles a termite hill than an Egyptian pyramid. They operate on the boundary between order and disorder. They can appear to operate quite stably for some time and seem to be in equilibrium. However, they are continuously adapting to their environment. When a perturbation occurs, earthquake, for instance, or a tsunami, complex systems go into what's called the critical condition and undergo a phase transition. And in that case, a phase transition would be like ice melting into water or water boiling into steam. That's all phase transitions. This could move them from an equilibrium state into a crisis situation. The dislodging of a single grain of a sand pile can cause an avalanche and the whole structure to collapse. And people carried out, in fact, experiments on sand piles, and they simulated them on computers. I'll try to bring that to your attention so that you would be able maybe to research more in systems theory. Complex system, the more the system is complex and having too many organized components, the more it is fragile. Fragile meaning that it can break with any small perturbation. And things can fall apart quickly when any unforeseen event occurs or a sequence of events. And the damage or the consequences can be more severe if it is subject to more than one single event. Systems that do not have enough redundancies, this is our way of dealing with, to build strong or solid systems that can withstand perturbances from the environment. So redundancies are part of the design of the system. We'll see that when we study fault tree analysis and event tree analysis. And they would be more reliable and less fragile if we add those redundancy. Richard Feynman, a very great scientist that you can find his lecture notes on physics in the library, the physics library. He wrote a book, Physics is Simple. In fact, he suggests that classical physics deals with inanimate objects performing simple behaviors. Example, the pendulum. We can describe the motion of the pendulum of a spring or a simple harmonic oscillator with a very simple differential equation. And even the equation of the heavenly bodies, the planets around the stars, atoms and molecules, radioactive decay, relativistic quantum behavior, are governed by very simple deterministic equations. But the real world is much more complex than those simple equations that physics provides us with. So we have basically an incomplete knowledge according to the level of complexity of systems that we use. So in that case, you find that complexity deals with the topics of accident analysis, even weather forecasting, biology, mathematics. All of them need new tools for analysis because these systems cannot be predicted with our very simple deterministic equation. Existing conventional statistical models assume that rare events, or what people like to call the statistical outliers, and this would be the tails of statistical distributions. If, by that, I mean that if you have, say, distribution like the normal distribution like this, which has a mean, it has a variance. So this is what we call mu here. This is the variance sigma. These events that happen here at the tails here are not really given due consideration. And this is where the very serious accidents with large consequences, in fact, occur. Later on in the chapter, we are going to call them the black swans, according to an economist, Taleb is his name. I'll try to explain it to you. So these rare events or statistical outlier have a substantially lower probability of occurrence by definition. However, their consequences can be quite large in general. So in current statistics and probability theory, we use the concept of the mean value or the mean or the mathematical expectation in the middle of our normal distribution, and the concept of a standard deviation to describe events that are random in nature. Now, we are interested in accidents, so what's called the bell curve. Here is a bell curve. It looks like a bell, inverted bell. This is also called the normal distribution, as you know. It's also called it's a normal distribution or the bell curve. It tells us basically that the less probable, the extreme events at the tails there occur very little, but unfortunately they have the largest consequence. So in the latest decades, the field of mathematics started dealing with complex areas of science. And in that case, the analysis of non-linear systems dealing with complexity. Many authors can be accessed. James Gleick in 1988 wrote the book Chaos, and he introduced what's called chaos theory. Roger Lewin, another book, Complexity, introduced complexity theory. And that is really what describes, unfortunately, events in general. This is an event that happened in Minneapolis. I chose that event because I drove on that bridge myself, and you could see how the bridge simply collapsed at Highway I-35 on the Mississippi River. In 2007, the whole bridge collapsed, killing 13 people who are commuting to work. And I drove on it during the winter when it was icy and injured 145 motorists. They built another bridge to replace it at a cost of $250 million. And unfortunately, we know, according to the American Society of Civil Engineers and the Federal Highway Administration, that 1 out of every 4 600,000 bridges in the United States are either inadequate or outdated. So this is really infrastructure that was built a long time ago, but it's failing and subjecting members of the public to accidents. There are some problems in complexity theory that do not have a solution. In fact, you cannot have a solution, physical solution for them. And that comes to some mathematicians, like the French Poincaré is his name, and that is the three-body problem. So if you have a system, let's say, of 3 planets or 3 stars interacting in the heavens with each other, that problem has no solution. You can get many, many different solutions, but not a single solution. You'll find no applicable algorithm that a human would discover to adapt successfully and turn basis uncertainty into basis risk. And the 3-body problem doesn't have a general closed form solution. And if you don't believe me, go to the physics library. They have some books on the 3-body problem. People attempted, but doesn't have a solution. So in 1887, Henri Poincaré proved that the motion of 3 objects, with the exception of a few special starting cases, is non-repeating. So it doesn't have a solution. And basically, this is what you call a chaotic system, chaos. Chaos is not the same as randomness. Randomness is something that can repeat itself, but chaos is something that we cannot say it repeats itself. Another gentleman, Mark Buchanan, suggested that complexity has an extension that he named ubiquity. And ubiquity explains the behavior of systems in a critical state, and we'll describe criticality as we go around. The basic principle of ubiquity, according to Mark Buchanan, are that they have a power function. And we know of really one main power function that we'll try to deal with today that predicts the size of earthquakes. These are called power functions. And experiments, as I said, simulations on computers. And I'll give you an experiment to carry on yourself to check that chaos theory, that if you add a single grain of sand to a pile of sand, or maybe to just grains of rice or wheat, you'll find that the addition of a single grain, meaning that a single perturbation to the pile of sand or grain can have 4 different consequences. You can get no substantial effect, but you'll see in an experiment that I'll ask you to perform yourself, it may precipitate a small avalanche, or it may precipitate a large avalanche, or a series of avalanches leading eventually to the total collapse of the whole structure. So unfortunately, this is a model of how accidents happen. So in that case, to anticipate accidents in the human endeavor in general, or prediction of these consequences is a daunting and a very, very challenging task. However, one could identify and measure what we call the precursor states. There are some states that occur before the collapse occurred. And in that case, you find that we are dealing here with a probability theory and possibility theory, and a coupled probability possibility theory as we try to develop to predict or to anticipate nuclear accidents rather than simply reacting to them when they happen. All right, so let's study in more detail this concept of criticality, the complexity theory, and equilibrium and non-equilibrium system. I'll go fast because this chapter really needs some interesting reading here. I cannot, I'll suggest that you read the text, but this is an event that happened next to us here. You might recognize a situation that happened at Indianapolis, right west of us, capital of Indiana. They had the Indianapolis State Fair, and it resulted from a storm on August 13, 2011. Everything was fine. People were sitting there in a stand, as you could see here, watching a band play on the stand. And suddenly a gust of wind just simply occurred out of nowhere. As you could see, these are video grabs of the event. People took a video of it. The whole stage collapsed, and the people sitting in the front rows were affected, and it caused 5 people to die. So that's an event that was totally unexpected, caused by a gust of wind. So you'll find that complex adaptive systems have the tendency to move in ways that are totally unpredictable in general, quite suddenly. And they function in an apparent equilibrium for some unknowable period, and then, quite abruptly, they collapse. Mark Buchanan, if you read his quotes and his text, examines interesting yet tentative ideas of chaos, complexity, and critical state in his thought-provoking book. You may find it at the library, Ubiquity, Why Catastrophes Happen. And he tries to explain the concept from theoretical physics designated as self-organized criticality. I'll show you some examples of that criticality and that system collapses from equilibrium. This is another case of a sudden event that happened due maybe to flooding or simply to a crack happening in a dam in Ireland. Notice that people never expected for that dam to collapse. They built their homes here and their farms, and lo and behold, you find that the whole dam collapses and those homes probably have been totally decimated. Complexity theory has a tie-up with something that you may have read about that's called the butterfly effect. That's a concept from chaos theory. It suggests that, say, a butterfly simply flapping its wings all the way maybe in South America affects maybe or generates a storm here in our Midwest. So there is a possibility, not a probability because we cannot measure it, that is construed as a probability. That's not a probability, as I say, that a butterfly flapping in wings in South America can cause a storm in Europe weeks later. However, that same butterfly can flap inside a closed balloon with no effects whatsoever. And this has to do that the air inside the balloon is in equilibrium. So here we have to deal with the concept of stable equilibrium, unstable equilibrium, and no equilibrium at all. Mark Buchanan describes these ideas of collapse of complex systems in terms of constructions on simulations on computers, or an actual construction of grains of sand. So, and by dropping a single grain of sand after another in an hourglass or on top of a table leads to the development of a pile of grain of sand. The pile grows larger and larger until one side of the pile starts an avalanche by the effect of the addition of one single grain of sand. One single grain of sand can cause the catastrophe of a system that has reached the condition that we call criticality condition. Most of the time, the avalanche is a small one. Sometimes, though, the avalanche builds up to a large one, leading to the collapse of the whole side of the pile. And that is what happened at that bridge in Minnesota, and the collapsing, actually the collapse of the Twin Towers of World Trade Center. They were designed to hit to get a plane to hit them without collapsing, yet a collapse occurred. People tried to develop theory on the size and timing of a cataclysm, and they have basically what they call the frequency kind of laws, or fingerprint laws. They describe it by a power spectrum. I'm going simply to go to experiments, the experiments of sand. So this is an experiment simulated on a computer where you have basically a square with 100 pixels on the side. And then randomly, you sample a point on the x-axis, and you sample another point on the y-axis. You generate a random number from 0 to 1, multiply it by 100, and that gives you a point in that pixel of points in the plane. And then you keep adding points and simulating that you are dropping grains of sand on now what has formed here as a pile, another pile, another pile, another pile of the sand. And then you find that, and you set up some rules on when a grain of sand would cause a collapse, depending on its adherence to the neighboring points. And 3 people did research on them from basically Long Island here in New York. And they studied how a single grain of sand can cause a collapse of the whole pile. So these are designated as sand pile simulations. And I'm going to jump to the end of the chapter today, and you'll have fun doing it. I'm going to invite you to carry out an experiment that Back, Cow, and Kurt conducted on a computer by getting actually a shoebox, placing in it some sand up to the edge, or maybe some grains of rice, kernels of rice, and then let it dry in the sun, and then keep adding single grains of sand. If you have a critical situation where the slope is in a critical state, a single grain of sand would let the whole thing collapse. And this has to do with what we call self-organized critical system. And I'll show you some critical systems in a moment as we proceed in the lecture right now. All right, so in that case, sand pile simulations were used to simulate that effect where systems get into a critical state. Again, according to Mark Buchanan, but by the way, Mark Buchanan was not meaning to describe nuclear accidents or bridge collapses or flooding or hurricanes. He was interested in making money on the stock market. So in that case, what he's trying to simulate is a possibility of a financial system or an economic system collapsing. So he is telling us here to find out why such unpredictability should show up in their signed pile game. Beck and colleagues next played a trick with their computer. Imagine peering down on the pile from above and coloring it according to its steepness. Where it is relatively flat and stable, color it green. Where steep and in an avalanche terms, ready to go, color it red. They tell us really here how you can, on a computer, simulate that system that collapses after getting into a critical state. With more grains, the scattering of red danger spots grew until a dense skeleton of instability ran through the pile. Here, when then was a clue to its peculiar behavior. A grain falling on a red spot can, by domino-like action, cause sliding at other nearby spots. If the red network was sparse and all troubled spots were well isolated from one the other, then a single grain could have only limited repercussions. But when the red spot comes to riddle the pile, the consequences of next grain becomes fiendishly unpredictable. It might trigger only a few tumblings, fine, or it might instead set off a cataclysmic chain reaction involving millions of those little grains of sand. The sand pile seemed to have configured itself into what we call a hypersensitive and peculiarly unstable condition in which the next single perturbation, in that case, a single grain of sand can trigger a response of any size whatsoever, and this is unpredictable in that case. There are different modes of stability that we think about when accidents occur, and that graph describes it to us. How do we define a system that's stable? This is shown here at the bottom of the valley in between two mountains. When you have a ball there, a stable system is a system that is, if it's given a perturbation, whether up to the right or to the left, it is fail-safe in the sense that it comes back to the bottom. So this is a description of what we call a stable system in terms of accidents and occurrences. If it's, on the other hand, it is not contained in a valley, think about it as a valley here. If it's contained on the top of the mountain, any perturbation would make it fall to a stable state, interesting enough, or to a metastable state. So in that case, this is what we define as unstable equilibrium. It is an equilibrium, but it's unstable. It doesn't last too long. This is equilibrium that lasts forever because it will always go back upon perturbation to the bottom of the valley. A metastable state is defined as a system that can move, given a perturbation, either above a peak and come down to a stable state right here, or move to an unstable state. So we have three definitions here of stable, unstable, and metastable. So metastable is a system that doesn't know really whether it's going to be unstable or whether it's going to be stable in general. And one source of this instability is complacency. And we'll discuss that later on in terms of actual accidents. The Chernobyl accident, for instance, was a situation where complacency was the ruling event or a human error that occurred in that case. All right, so we talk here about systems before they collapse, going through what we call a critical state. So what is a critical state? We look at two examples instead of reading the material. This is an experiment that you can see usually shown maybe on YouTube, where people collected ping pong balls. They set them on mouse traps. Each one of those is a mouse trap with a ping pong ball on it. And then they created a perturbation. And all they did is throw a single ping pong ball on that collection of mouse traps with a ping pong ball. And this is exactly what happens. Immediately, there is basically contagion. One trap flips out, and then you'll find that those balls go and affect the whole system, and the whole system now is a system of flying mouse traps and ping pong balls. So that system is in a critical state, and this is our only hope. really to detect accidents before they happen. We must be able to identify those critical states and simply restore the system back into a stable configuration. Another example is an example of in dominoes. You get up some domino kind of a single domino. Let's call each one of the single dominoes here standing up on their side. And you'd consider, if you consider the one that's 3 and 4 here, all by itself within a forest of dominoes, it's stable. Nothing is happening to it. But give it a perturbation from one side, and that domino, of course, the domino effect gets to the collapse of the whole line of dominoes. This is basically seeing the forest or the tree. The 7 domino alone appears stable in an overall system in a critical state, but it may be not really stable. It may be on the verge of collapse. Can we have some kind of a law that describes those events? There is only what people call the power laws that can describe these events other than computer simulations here. And let's see here if I have that form of the law. It's called the power law. I think we'll come to it later on. And it has been applied successfully, in fact, to the situation of predicting the size of earthquakes. So I'll leave this and give you that law. This is what we call a probability density function. And the observation is that when you get earthquakes, you'll find that large earthquakes are 4 times less likely to happen when their energy release is 4 times less. They're 4 times less likely to occur when their energy is doubly larger than another earthquake. And the power function in that case of probability density function is P of E dE is equal E naught over E squared dE. And that is for E larger or equal to E naught. So when you want to calculate the probability of an earthquake, you take the integral of that quantity, but the lower limit of that integral, well, the earthquake has to generate some energy. So if we write that law here, P of E dE, and you want to calculate the probability of the occurrence of an earthquake, you have to integrate from a lower limit E naught to some E here, and then we have that E sub 0 again divided into E squared. And when you integrate this over dE for E larger than equal than E sub 0, you can calculate the probability of an earthquake occurring. Notice that this is a continuous probability density function and an example for probability distribution. Now, when it is discrete, we call it a probability distribution. Oh, one of them is a very simple probability of heads and tails. If you flip a coin or edge, this is 1/2, 1/2, and this is 0, and we can call this the probability of HTH maybe for flipping a coin. Notice that the probabilities here can be larger or equal to 1, and the sum of these probability P sub I from 1 to 3 should be equal to 1. So this is a probability distribution on its discrete. This is a continuous distribution, so we call it a probability density function. And other probability density function will deal with this as we proceed further and learn more about probability distribution and probability, the Boolean algebras and the Morgan algebra. I'll give you a simple assignment for tonight to integrate that function and prove that it is a probability density function. How do you prove it's a probability density function? Oh, you prove that the sum or the integral of the probabilities is equal to 1. So you take that E sub 0 here outside the integral, and then you integrate 1 over E squared. That's E to the minus 2. Minus 2 gets plus 1 divided into E naught, and then integrate from the upper limit to the lower limit. It should be equal to 1. So just check it out, and go through a very simple exercise. This idea of gives us an idea that says that if you calculate or expect a large earthquake that is double an initial earthquake that releases an energy E sub 0, you'll find that it goes 1 over E squared, meaning that it is 4 times less probable to occur. Large earthquakes occur very, very rarely. The one at Fukushima, as we'll see later, was so powerful, it was equivalent to hundreds of megatons of nuclear devices power, or 10 times maybe the energy release from the volcanic eruption of Mount St. Helens. Other experiments that you can have fun doing is get potatoes. They took potatoes, in fact, and they froze the potatoes. What happens if you get a hammer and hit a frozen potato? You'll find that it will disintegrate into many, many pieces. And when you count the large pieces compared to the small pieces, you'll find that 1 over the size squared, the energy release squared, applies. So another experimental study determined the power law distribution of the sizes of the shards produced when a frozen potato is shattered. The study was carried in Sweden, I think, out by it's in Denmark. Danish physicists in 1993. They counted the shards ranging in size from 100 grams down to 1,000th of a gram and found that doubling the size of a shard makes it 6 times as rare. And earthquakes that are also large in size, say that E sub 0 would be 4 times less probable. And this is the only way that we can describe those cataclysmic events when earthquakes happen. We don't have really much knowledge from system theory to clarify the events even more. As I suggested, the fingers of stability are our only hope when they form, if we detect them, to predict that avalanche is going to happen later on. Some theory has been also developed in what's called the Nash equilibrium and the Macaulay's disequilibrium. Nash was actually he obtained the Nobel Prize in what's called game theory, the theory of games. And the equilibrium is named the Nash equilibrium. It is a strategy when people play games. Well, what's playing games? When they interact with each other in peace, in negotiation maybe, or in trade, or even in war. And the idea is that people can get an optimal strategy for games involving 2 or more players, whereby the players each reach an outcome to their mutual advantage in general. In the sandpile problem, we end up with a critical state that people call a stable disequilibrium. Disequilibrium, not equilibrium, disequilibrium. Each player works hard to maximize his own personal outcome to reduce his exposure to the finger of stability. There was a movie, by the way, that you may like to rent and watch about John Nash. He was really a genius, but he had a handicap, but he ended up with a Nobel Prize for his genius in mathematics. Accidents also can happen in what we call the black swans. Anybody heard about black swans again in the class? So this is interesting knowledge here. When the early settlers started moving out of Europe to the New World here, the Americas and Australias, they suggested that there are no black swans that can occur anywhere in the world. They were used only in Europe to having white swans in the ponds, or that royalty and princes built around their mansions or chateau, castles. And however, they discovered when they went to Australia that indeed there are also black swans. So black swan comes in to describe today the occurrence of events that are really rare, or these events are the outlines of the normal distribution, things that happen very, 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 very rarely, and that we have very limited ways of predicting them. Another name for it is also called rogue waves, and rogue waves do happen. Some people suggest that the Bermuda Triangle is a region that's very dangerous for ships, because sometimes those rogue waves do occur there, and if they hit the ship sideways, that's done for the ship, and they have many, many wrecks in the Bermuda Triangle along this line. So the developer of this idea is an economist here in the United States, Nassim Taleb. He suggests basically that the occurrence of highly improbable events is something that we have to worry about. And I'll quote one of his quotes here, but I recommend that you read the next of the text. Quote, "But we act as though we are able to predict historical events, or even worse, as if we are able to change the course of history. We produce 30-year projection of social security deficits and oil prices without realizing that we cannot even predict these for next summer, or our cumulative prediction errors for political and economic events are so monstrous that every time I look at the empirical record, I have to pinch myself to verify that I'm not dreaming. What is surprising is not the magnitude of our forecast errors, but our absence of awareness of it. This is all the more worrisome when we engage in deadly conflicts. Wars are fundamentally unpredictable, and we do not know it. Owing to this misunderstanding of the causal chains between policy and actions, we can easily trigger black swans thanks to aggressive ignorance, like a child playing with a chemistry kit. And we are living that today. You can really relate it to the occurrence of the Ukraine-Russia war. When the Russians started it, they never, ever thought that it can turn to the situation that is very dangerous today, threatening the whole world with a nuclear war and the human race by extinction. So this is the concept of the black swans that also are used to describe events that are not predictable. He tries to apply the idea to a collapse of the stock market. These guys worry about making money more than us engineers. We worry about preventing accident. Some people talk also about gray swans. Black swans are no different than rogue waves, as I suggested, that sank many ships in the Bermuda Triangle as an example. And this is an example that happened in the North Sea. You could see here that this is the height of waves in storms, but one of them, you could see here, reached a height of about 18 meters in height. And it affected one of those oil rigs in Norway. And the time span of that rogue wave was 10 minutes. And I'm not sure whether it led to the deaths of people, but basically the oil rig was able to withstand it's a huge in size, obviously, that rogue wave. So in that case, we are also talking about what is seen and unseen events. So in that case, sometimes we think about the possibility of events occurring, but some other events, the outliers here in particular, cannot be seen. And a French economist or philosopher, Bastiat, simply came up with a very interesting example for this here. Let me give you the example. He suggested that you are in a savanna and you have to go through that little creek here, and you have to worry about lions. So do you see the lions in that picture? Somebody answer me. You see one lion here, right? You see one lion there? Do you see any other lions? No. He suggests that, okay, you would avoid those two lions here because you see them, right? But then look here in this area here, and he shows us that hidden there and not shown to us is another lion. So we could avoid what we see, but then we can fall into the risk from what the unseen in a given way. So this is all a situation where accidents occur, and I found myself also some interesting picture that I'll share with you. If you go out west, say hiking on a trail, you can face what a philosopher at MIT, Minsky, names as or called the Minsky moment. situation where basically grizzly bear comes and faces you. The Minsky moment occurs when we are complacent in running our engineering system or our economical system. We don't worry about the bad situation that can occur, and then we are faced with them, and when they occur, disaster happen or does not happen. This is another situation here. Surfers in the water. What do you see in the water there? A shark right here. And it is not pie in the sky. Another picture shows here somebody basically surfing in California. Here is a wave breaking, but look at that fin here. The big shark was coming at him without basically the unseen. That's the idea of a Minsky moment. And the shark, in fact, attacked him and bit the board on which he was surfing. And luckily, he survived the whole thing. This is, again, Minsky moment. Minsky is a philosopher, as I said, at MIT that suggests that complacency, the more we are sure about an event, about a situation being safe, the more instability builds into it, and eventually that complacency leads to disaster. And that's what happened maybe at the 3 Mile Island situation in general. So he, Nassim Taleb, the one who introduced the concept of the black swan. By the way, you can read a book by the title Black Swan. I had the book myself. I lended it to somebody who never returned it to me. He liked it so much, but you can get it from the library or from a bookstore. Some other events can lead to collapses and accidents. Occurrence is the concept of herd behavior, copycatting versus pack behavior, flock behavior. And in a way that can explain why is it that some people lose their mind and start shooting other people that they are angry at post offices, for instance, or in schools, in fact. And then you find other people copycatting them. So this is also another source of the occurrence of undesirable events in our complex society in general. We should be aware of these ideas. The mathematical models describing how to avoid catastrophes do not really exist. I repeat that, do not really exist yet in the mathematical realm. Some of you may develop new ideas, but at least you can get some inspiration from what we know about earthquakes, about shattering potatoes, frozen potatoes with a hammer. Earth scientists believe that critical state theorists are overreaching when they try to liken the behavior of something as complicated as the Earth's crust, meaning the occurrence of earthquakes or volcanoes, to a pile of sand. We cannot argue this, but the technique is employed to explain forest fires, stock market fluctuations, mass extinctions, and upheavals in human history. For instance, a black swan could have been the assassination of the Archduke of Serbia that caused the beginning of the First World War, if you read about history in that case. Maybe we will classify the behavior of Mr. Putin invading Ukraine as one of those miscalculations and the occurrence of a Minsky moment. So considering the glimmer of the positive, Nassim Taleb states, quote, "We are gliding into disorder, but not necessarily bad disorder. This implies that we'll see more period of calm and stability, with most problems concentrated into a small number of black swan." We may be believing a black swan, but at least we know what are the situations of the critical state that can lead to instability. Our goal should be anticipating specific undesirable consequences that could be studied. And if we are able to predict or identify the precursor to the occurrence of the undesirable events, earthquakes and volcanoes and so on, then we can provide society with a tool to deal with disasters in general. Again, here I give you in that appendix a way to build up that very simple experiment yourself and see for yourself that a simple perturbation can lead to a total collapse of a system that is in the critical state. And I'll stop here and I'll stop the recording, and I hope that it succeeded, because